1 constant velocity for Physics 2211. The purpose of the lab was to observe the motion of an object moving at constant velocity and compare it to a computational model to find more about Newton's second law. For this experiment, I used a tennis ball which was rolled across the dining table. The main result of the lab was that the computational model's constant velocity was very close to the experimental constant velocity, with the experimental one being slightly slower than the model's constant velocity. According to Newton's second law, the acceleration of an object is equal to the net force divided by the mass of an object. Rearranging the equation 1 on the right gives equation 2, which is a velocity update formula. With the key assumption that net force equals 0 and frictional and air resistance forces are negligible, we get equation 3 where the F-net factor becomes 0 and cancels out of the equation. So it's Vf equals Vi, which is the constant velocity. We also used the equation 4, which is the position update formula, and with this, the model becomes simplified and becomes Newton's first law, which states that an object with constant velocity stays at constant velocity unless acted upon by an external net force, which in this case doesn't happen as we have already assumed the net force is 0. So the system was the tennis ball, which was on the table surface. The surroundings were everything outside of system, including the normal force from the table, air resistance, frictional force, or gravitational force downwards. And so in the first part, I created a video of a moving tennis ball on the table, uploaded it to Tracker, specified the video frames 44 to 64 where the ball was in constant velocity, as well as calibrated, as you can see in figure 1 here, using the diameter of the tennis ball. I also chose a coordinate system as shown here in this figure, where upwards was plus y, down was minus y, to the right was plus x, to the left was minus x, and the center of the tennis ball was the origin. And in the video, the tennis ball moved to the left or moved towards the negative x-axis. So in the experiment, I next identified the object's position in each of the video frames, as you can see in the video here, for 20 frames, and the x-axis position and time were graphed using the Tracker software. Initial conditions: the observed start time was 0 seconds, 0.667 was the time of last observation, and we also had the ball initial position vector, which you can see here, as well as the another data point to find the ball's initial velocity, which was delta r by delta t, and we used this vector minus this other vector to get negative 0.673 meters per second. So you can see here the time versus x-axis for the Tracker software, as well as the graph position versus time. For the computational modeling using GlowScript, this chunk of code right here shows visualizes the ball trail and graphing of the data. This code initializes the mass of the tennis ball. This ball.POS is the initial position vector, and the ball.VAL is the initial velocity vector, and this updates the time, this code over here. Next, I had a while loop which had the final time constraint, as well as F-net being set to 0 as net force is assumed to be 0, as well as the velocity update and position update formula from Newton's second law. And then the time was updated in each iteration along with the curve being updated. So using the computational modeling, figure 4 and figure 5 show the position versus time and the velocity versus time graphs that was generated by GlowScript. And this was the GlowScript output for the ball's movement. So the results, the experimental results, had a constant velocity of negative 0.651 meters per second, and the computational model had a constant velocity of negative 0.673 meters per second. As you can see in the graph here, the model and the experimental are pretty close together. Towards the end, the experimental velocity is slightly slower than the model's velocity, and the constant velocity is obviously the slope of the position versus time graph here. So for some discussion, the experimental constant velocity was approximately the same as the computational model's constant velocity, although there were slight differences towards the last frames. So from physics principles, both models were similar in the beginning, but the experimental model's constant velocity slows down due to frictional force causing a net force on the system, and a net force changes velocity as per Newton's first law, as net force now is not 0. And from Newton's second law, the F-net part of the equation is now non-zero as well, which means that the velocity will now not be constant, and this causes differences between the model and experimental predictions, as frictional force was assumed to be negligible in the model, but now it's non-negligible. So what if I were to flip the axes? Flipping the axes would cause the object to be going in the positive x-axis direction, which makes the graph to be upwards with the same slope, but in the positive direction instead of the negative direction. And the speed will be the same, but velocity will be different as direction is opposite. So what does it mean? The net force is 0, resulting in constant velocity in the model, because the gravity pushing down on the ball and the normal force from the table pushing up on the ball cancels each other out, and so the ball continues on the same velocity as per Newton's first law. But we had assumed that friction is negligible, but soon in the later parts of the time, the later frames, the friction becomes non-negligible and significantly slows down the ball, causing a non-zero net force in the direction opposite to the ball's constant velocity and creating a non-constant velocity. So in conclusion, the experimental and model results closely matched each other with slight differences attributed to frictional force coming into play with increasing time. Possible sources of error include that when selecting point mass for each frame and tracker, there might have been slight inaccuracies in choosing the exact place on the ball, resulting in deviations from real data, and another error could have been in selecting the exact frame where the ball wasn't speeding up or slowing down and was at constant velocity. So that's it for Lab 1, and thank you for watching.